Guys, in this video we're gonna go discussing the reverse diffusion processes in the diffusion models. So in the previous video we understand the forward diffusion processes and let's go into the reverse diffusion processes. So in the forward diffusion process, what you do is just take this image and add Gaussian noise iteratively. It can be 1,000 times step times. We can just add the noise into 100 times step or 1,000 times step. This depends. It depends. So and you just add noise and destroy the structure of the data when moving from the real data, which is from a data set, and you just add noise and you actually convert this into a pure noise which is sampled from this distribution having mean zero and unit variance. So and this is the your prior distribution, and this has this form. So this is a pure Gaussian, and this has this functional form. This is the defined by this distribution, this conditional distribution q of xt given xt minus 1. So and it can be written as this form. So you can get xt by multiplying this quantity with the previous image pixel values. So this is the mean of a distribution, and this is the variance. That is the variance of your distribution. So mu theta, I can just write it like this. Mu theta, and this you can write this I. So and this is your distribution. And let's move into the what is this quantity? This what is this term? This distribution is actually this distribution is your neural network, which is a denoiser. So you can just denoiser. This is denoiser which take this image and denoise and give this image, not directly, but it will give less noisy image than this image, and it will denoise iteratively, not at one step or one pass. So it will take noisy image, make it less noisy, and take that image and make less noisy. So this distribution actually take this two quantity here, this quantity, and this will denoise the image. So it will take the not this will just give this. So it will take the more noisy image and give less noisy image, so at each step. So and this is our denoiser or our model, which which is actually a mu theta predictor, or the which is actually mean predictor or the variance predictor. So and this is actually the this will predict these two quantity of the distribution. So and and we have to define another thing also here. So if we are getting more noisy image, so taking this and we are getting more noisy image xt given this images from this distribution. And if you can just reverse this distribution, xt minus 1 given xt minus 1 given mm, xt. So this would be very nice if you just reverse the distribution and reverse this uh, the reverse forward diffusion. This is actually the actual reverse distributions, but it is not computable. So we'll approximate using this neural networks p theta of xt. This is our actual, but we can't compute this quantity, and we'll approximate using our neural network p theta. So and this quantity here qt minus 1 and xt is not tractable. So I'll write not tractable. So we will use our neural network to predict this reverse distributions, and this can be used in our training, when we are training. So we have to take care of it. So I can just write it so that and so let's deep dive into the reverse diffusion process. We understand what forward diffusion processes is, and it's time to understand the reverse diffusion processes. So we want we want to make the neural network p theta, which will take this images, this x this xt minus 1, and it will give this xt. So we want to make this neural network, and this can be obtained. So this distribution can be obtained by learning the mu theta. So we have to approximate this. For this distribution, we will find the mean and the variance. So for this distribution, we will find these two things: this variance and the mean of the distribution. So if you able to predict this mean and the variance of this distribution, this distribution, if you find this mean and variance of this distribution, we can actually do this reverse transition. So if we find this the mean and the variance of this transition, so we can just compute this mean and this variance, and we can actually denoise our images by predicting this mean and this variance. So we'll see how we can do that, and for that I'm going to be using this block. So this is very consumable and it's easy to consume block. So I'll just tell you. So what you're doing here is actually, if we can reverse the forward processes and sample from this distribution. This is the actual reverse distribution. This is not our neural network, but this is the actual, this is the opposite of our forward processes. And it is nice if you just take some noise from this standard distribution and pass it through this distribution and get this. That's not, we are not passing. So if you can just reverse this distribution q xt minus 1 and xt, so we can get the images which actually resemble the data of our training data. So and we can't estimate this because it need to use the entire data set, and therefore we need to learn the mapping. We need to learn a model p theta to approximate this conditional probability under in order to run this reverse diffusion processes. So we need to approximate. We can't compute this. This is intractable actually. So and we need to approximate by our. We're gonna go create our own distribution, which will try to mimic this distribution. And this is actually a mimicker of this distribution. So and this is our actually the forward reverse diffusion joint probability. This is a joint probability of the reverse distribution. So and this can be written as this p of xt. This is our pure. So we are sampling. This is just sampling from the. Just we are just getting the probability of the. We are just taking the from this distribution this prior. So we are just taking the standard. We're just sampling this xt from this distribution. So and we are just multiplying this from 1 to t, and just we multiplying this p theta of xt minus 1 and xt, will get this joint reverse distribution, and this quantity is actually can be written as the Gaussian. So because we consider note that beta t is small enough, so this quantity, this reverse actual reverse will be also be a the also the reverse transition will also be a Gaussian. And because we are approximating it, so we can also take this function, this p theta can also, we can just take it as the same functional form as this. So because we are approximating it, so we can take this functional form. And and this is the R. It is noteworthy that the reverse conditional distribution is tractable when condition on x0. So this actual reverse conditional distribution is actually tractable when we count the condition on x0, and it has the Gaussian. So as we have already discussed, so and this has this form. This will, and this has mu tilt and beta tilt, and this, and you have to just this is the actual transition reverse transition of the forward processes. But so it has mu tilt and beta tilt, but for our predicted reverse transition we have mu theta and the covariance theta. So this is the variance and the mean of the distribution. So and and we are just taking this term here, just taking this term, and what you're doing here actually is, so I'll just plug it. So we are just applying the base rule here, and if you again apply some property of algebra and just simplify it, and I'm not gonna go telling you the other simplification right now. So and and the and just applies this reparameterization trick. this alpha t is equal to 1 minus beta t, and alpha bar t is actually the product, cumulative product of this alpha t. And we actually get this beta t, the actual reverse conditional distributions. When condition x 0, we get this beta t as this quantity which we'll need. So this is our quantity, beta tilt of the beta tilt, and this is the our mean of the uh, reverse conditional distribution. So this is the mean, and we does not have the access to x 0, so we will just uh, replace this x0 in terms of xt, because we can actually predict xt. And why this word from this come is actually, we can just we can just predict xt is given x0, so we can just the substitute, just change the order and just get x0 separate, and we get this term here. So and we plug it into the above equations, and we obtain this mu tilde as this quantity, uh, which is which is just actually, this is a noise added at this time step, and we are just scaling it and just subtracting this, and again scaling this. So and we train this model by optimizing the variational lower bound. So and this is our variational lower bound here. So by starting from this log likelihood of the alpha for data, and we are just making a bound, so this become our bound. And we can just apply the Janssen inequality. So we want to minimize the cross entropy. So to minimize the cross entropy, so we can also use this learning objective as this cross entropies, and we also get this bound, variation lower bound. And to convert each term in the equation to be analytically computable, the objective can be further rewritten to be a combination of several KL divergence entropy terms. So and taking this lower bound, and if we do some calculation here, and just this joint, we are just open this joint using multiplication and applying the log property here, and we actually get this term which is a which has a lower variance this term. And this has three terms mainly, this first KL, second and third KL. So and less level is component into a variational lower bound lost separately, and this has this term. So where lt minus 1 and l0, and from t2 to t, so we have this dot here. And let's understand what this lt is actually the KL divergence between the forward processes. So this is, we are just giving x0 and we are just predicting xt. So this is our actually a forward processes, and this is our prior distribution, so p theta of xt. So and we doesn't need any parameters to learn this sampling. This is just a, we're just sampling this xt, which we know, and this will be from the Gaussian distribution. So there is nothing to learn here. This is our forward process, and this is, we're just sampling xt, which is a Gaussian noise, so we doesn't have to learn this. So this term is actually constant, and we does not care when training our model. So this KL divergence get omitted from here, this term is omitted from here, so we doesn't need it. And lt is actually the main component here. So this is actually the KL divergence between the actual, this is the actual reverse transition from noisier to less noisier, because we are getting xt from xt plus 1 when condition on x0. So just also conditioning on x0, and this is our model predicted reverse transition. We are getting xt given xt plus 1, and this is our lt, and this is our just the minus log p theta of. So we are just giving this is the probability of, just we are giving the second last image and getting the this is also reconstruction loss of the reconstruction from, we are giving the second last image and just doing computing the reconstruction loss, and we doesn't care this term as well. So we will just gonna focus on this lt for our training, for making our training objective. So for every term in LVLV except L0, so except L0, this term compared to Gaussian distribution, and thereby they can be computed in closed form. So we can just, because these are KL and they are just comparing Gaussians, and we can compute in closed form and use this for closed form while training. Uh, while training, and this lt is constant and we are just ignoring it as I've said. And because q has no learnable parameter, xt is just a Gaussian noise. L0 we can using a separate discrete decoder derived from this. So we can, this is also a different concept. So but we'll not gonna go look at it. So and we're just gonna go for our training objective, we'll just gonna go look at this objective. So and you can also use using a separate discrete decoder, you can derive from this. and and this lt minus 1 is our the thing for our actual loss, which we're gonna go implement, and which has been implemented in the DTPM implementation. So recall that we need to learn a neural network to approximate the conditional probability distribution in the reverse diffusion processes. So we want to learn this distribution. So learn this we want to learn the neural network to approximate this conditional distribution. So which has we gonna go get xt minus 1, which has from this mean and this variance. We could learn to train mu theta to predict this. So we are this will train the model to predict this, and this is our prediction, and we want this quantity to approximate this. This is the actual mean and this is our predicted mean, and we want this quantity become as close to as this, which is a real. And because xt is available as input at training time, we can reparameterize the Gaussian noise instead to make it predict epsilon t from the xt at the time step t. So we can just parameterize it. So mu theta we can reparameterize the Gaussian noise. So we can just, rather than predicting mean, we can just predict this noise here. So epsilon theta, so xt we are gonna go predicting actually mean, but we can just predict the this thing also, noise also, and what is actually going here. So we are just, this is our image and this is our just a scaling factor, and we are just subtracting this noise from this xt image. And xt minus 1 can be sampled from this distribution, which has this Gaussian functional form and having this mean and this variance. So and the loss term lt is parameterized to minimize the difference between the actual reverse transition mean and our predicted reverse transition mean. So this is we get during this quantity we get during training, and this is our predicted by the model. So we can just do this. So just write this formula what we have seen above. So there is formula. So this formula we can just plug it and write this, which I have already seen above. So this mu tilde t, which we have already seen, and this is just mu theta xt given also t. So and we are just writing this in this form, and which actually take this xt image, and we also giving this time step. So and if you just do some simplification and you just common out this scaling factor, this is just a constant, and there's nothing to there is because we are not learning this variance. This is constant, and we actually what we are doing here is, guys, we just passing this xt image at the time step xt and also time step, and we are predicting the noise and just subtracting it here. This is our actual, we already predicted it. This is our predicted noise. So and if you just take some common here, and you will get this term here. So you can just ignore this term here, which has been presented here, and this has been this work empirically better. uh, and we can just remove this waiting term here. So and our loss become this, what this loss is saying is, I will give you this. This is the real noise added at this time step. So this epsilon t is the noise added at this real time step t. This when we are doing forward diffusions, and this is the noise predicted by the model when we give the noisy image, and we give this time step t. time step t, and we are also giving this time step, and this is the noisy image, and it will just minimize is try to minimize in such a way that this noise predictor become better. This noise predictor which will take this to input, so this noise predictor will become better and better when we optimize this, and it will optimize over all the images over a data set, and we can just give this xt. So in terms of x0, which is our real image, so just multiplying this by this cumulative product root over of cumulative product of alpha t, and we can just rewrite this equation. We actually can, this is just value of xt. The value of xt is what we have already seen in the previous video. So xt is actually root over of alpha bar t x0 plus root over of 1 minus this quantity. So here, and we are just giving this t, and the final objective become like this. So this is lt simple, and where c is a constant not depending on theta, so this is just a constant. And this is our this is our reverse processes. So we actually, just I want to give you again a recap of it. So we started, we can't compute this quantity when we are inferencing, so this is actually intractable. And it's tractable when condition on x0, but when we are inferencing we doesn't have this x0. So when we are just trying to predict this image, so giving this random noise, we want to predict the real looking images which resemble the data, we doesn't have this x0. So we can't compute, we can just use when we are training this, when we are training our model, but while inferencing that can't be used. So we approximate this quantity by p theta. So we will, instead of this we will approximate the p theta, and we can just get the beta t and this mu beta tilt and the mu tilt of the actual reverse conditional probability. So and we can just use later on. So this beta t is actually this, and we are just using some reparameterization which I've already learned. So this, and this is applying base rule and just doing simplifications. So and we just because this mu tilt is actually depending on x0 here. So we want to just replace x0, because because we doesn't have we want to remove this x0. So this become only dependent on xt, so it can be used at this time step t. And so we optimize, so using the variational lower bound to the negative log likelihood, and we get this bound and variational bound, and we can also get from this Janssen inequality. And if you just do some, so opening it and doing some, applying some log property, we will actually get this variance reduction form, which have less variance. So this term is good for training, and we can just ignore this term, and this term we're just focusing on this term for our simple training objective, which is parameterization ability for our training loss. So and we're gonna go using this term only. So look at it here. So our mu theta become this quantity, which is which the mu theta will actually predict the noise added at the time step t given this image at xt. It will predict just a noise, and we are just minimizing the distance between the actual mean and the real mean. So and if we do some simplification here, we'll arrive at this term, and by simplification we obtain by, so empirically you can just remove this our weighting term, and we'll get this term which is a simple training objective. So this is our final objective we need